Hello, Patrick, can you hear us?
I can hear you.
Okay, perfect. Thank you. And can you see the screen?
Autonomous exploration of an unknown 3D environment.
Perfect. Thank you. Alors, on montrera le son après. It's okay. So we connected we saw the screen as well. It's working. So okay, so and I'm not able to see here. Yep. So everything is fine. Okay. Good luck. Thank you.
Hi Patrick. Patrice, hello. Steve here.
Hi there, everyone.
Okay, so Patrick, you have the Zoom for the jury session. Everything is right on your side, or?
I have a Zoom link. If it's correct or not, that's I guess we'll see.
Just if
But you sent it, yes.
Okay. Hello everyone. So let me first introduce myself. I am Olivier Stas, a research director at LAS France, and I will be the president of the jury for the PhD defense of Thibault Noel. Let me first introduce the member of the jury. So let me start by Professor Stephen Laval, professor from University of Oulu, who was one of the reviewers. Remotely, we have Professor Patrick Jensfeld, who is professor of KTH, Royal Institute of Technology in Sweden, who was also a reviewer of the PhD. One of the guests is Dr. Elena Olenikova, who is currently a senior researcher at ETH Zurich in Switzerland. And so I think the other member of the jury are the supervisor. So we have Eric Marchand, who is also professor at the University of Rennes, Professor Antoine LEHUGER, also at I apologize, at the Creative Engineering, and who is in charge of research and innovation inside Creative Engineering, and François CHAUMETTE, research director at Inria Rennes. So your PhD is entitled Autonomous Exploration of an Unknown 3D Environment, and you have 45 minutes.
Thank you. Hello everyone, and welcome to my PhD defense, where I'm going to be discussing the work I did during the past 3 years on autonomous exploration of an unknown 3D environment. I will start by quickly defining the topic. So here we are considering the high-level task of exploring an unknown environment. And so this task of exploration is it implies autonomous navigation to reach the parts of the environment we want to explore. It implies a notion of discovering areas of interest, and this asks the question of what criteria we want to define to determine what is interesting to see. And finally, it's a problem where we have at any time have a wide range of options to choose from, and so it comes up to a decision problem. Then the rest of the topic kind of describes the fashion in which we want to solve this exploration task. And so the autonomous aspect means that we are in the standard robotics setup. And so we want to have absolutely no operator intervention, and we are going to adopt a standard action perception. Then the environment is unknown, so it means that we have initially absolutely no data about it, and it asks the question of what sensing modalities we're going to use to acquire some data to build the environment model. And we are working in a 3D environment. So here in this work, we focus on indoors environments, and we are using only a 2D mobile base in reality. So it's a ground robot which drives on the floor. But we'll show during the presentation that some of our work can be extended to a 3D free-flying base, which we did in simulation. So from these definitions, we propose this definition of exploration as a composition of subtasks. So in the top left, you have the robot represented by the mobile base, which handles the actuation, and the sensors which handle the perception. Then the data from the sensors is passed on to the simultaneous localization and mapping brick, which provides the robot localization and the map of the environment. And then this map is passed on to the high-level strategy, which provides goals, which then are handled by the navigation block to actually plan paths towards the goal and execute the path on the robot. In this work, I chose to focus mainly on the path planning aspects and on the high-level strategy aspects. So the path planning is the essential brick in the rest of the system because it's highly coupled with the strategy as it provides the navigation path. It manages the local safety, the collision avoidance at the local level, and it is also responsible to plan efficiently in the sense that it should be computationally performant and also have provide paths of good quality in terms of depth, smoothness, and this kind of property. On the strategic side, we want to manage safety at the global context in the sense of we want to plan towards goals which are safe. And the two most goals of the strategy are to completely cover the environment as much as possible and to have a notion of long-term planning efficiency in the sense of not doing too much backtracking in the environment, going back and forth between areas of interest. And we can measure that as a proxy, for example, by the rate of data acquisition. For a bit more context about the work I did, so it took place in the Explore project. The Explore project is led by Groupe Créative jointly with Inria. And the goal is to autonomously reconstruct an indoors environment for VR purposes. So we have two sides in the project, the exploration side, on which I focus mainly, and the reconstruction side, which also takes into account some other problematics such as mesh reconstruction or mesh texturing. To go a bit further on just the Explore project, we have a lot of potential applications with the work I present here. So the most direct extension of what I present here is everything that has to do with building integrated models, either for digitalizing real estate or preserving cultural heritage or inspecting industrial sites, these kind of applications. We can then also autonomously operate in hazardous environments such as marine environments, space environments, urban search and rescue tasks. And finally, we can also think about other types of applications such as industrial prospection or military reconnaissance. So now I'm going to present quickly the outline of the presentation. I'm first going to focus on the state of the art to present what work has been done before me in the field. Then I'm going to focus on the planning task, or particularly focusing on safe navigation. And then I'm going to describe the latest exploration strategy we developed, which is a perception-aware strategy. So first, I'm going to start by the mapping aspect of the state of the art. So mapping takes place in the SLAM brick, which handles also not only the mapping, but also the localization. And SLAM systems come in many flavors, depending on the map representation. On the sensor they support, so usually we can find the SLAMs based on either LiDAR or cameras or a fusion of both. And they also rely on proprioceptive sensors such as odometry. And finally, many SLAM systems have very different data processing pipelines depending on their representation of the data. They are vision-based or 3D-based. And here on the right, you have a few examples of standard SLAM systems. The ones in bold are the ones that I used and tried during my PhD. Here I'm going to focus mainly on the type of map representation because for exploration, the main question on the map will be how can we exploit the data that's contained in the map to determine where to go next. So a first way of representing the map is to map the occupancy. Here the goal is to represent at any point in the space the probability of finding an obstacle. And so we can, in the literature, we usually find the two main ways to do this, either occupancy grid maps, as you can see on the left of the figure here. And more recently, a lot of work has been done also on continuous occupancy map, which can be sampled at any resolution. But as you can see on the right, they tend to be less sharp, and so for exploration they are less easy to use than grid maps. A second way of representing the environment, if you were here yesterday for the presentation of Ellen, you might know why this is in some ways a better representation. So it's the sign distance field representation, where here we want to represent at any point the distance to the closest obstacle. So it embeds more information about the local safety. And in the mathematical definition here, you can see that the point we take as a reference to the distance is called the witness point. Also, a good property of the sign distance field is that they are easy to compute the gradient for, which means that we can get easily a collision avoidance direction, and we can walk along the gradient easily. On the planning side now, so the main goal of a planning algorithm is to, from a start and the goal in the environment and the environment model, to find a feasible path that I call gamma, which connects the path and the start and the goal, sorry. And here, so of course, the main goal of the planner is to find a feasible path which doesn't collide with the obstacles, but we can have additional goals, such as having an optimal path as much as possible in terms of length, smoothness, or safety. And we can also want to put the priority on the query time performance. For certain applications, this is critical. It's not the case here, but I'm still mentioning it for completeness. And on the planning side, so I'm going to talk mainly about sampling-based approaches, which are usually nowadays they are one of the most common ways of approaching planning. So the idea here is to sample randomly some configurations in the workspace and to try and connect them until the start and the goal are connected by a path. So to do this, we usually use a graph-based representation named G with the vertices V and the edges V. And the first type of sampling-based approaches is the tree-based approaches, named mostly derived from the rapidly exploring random tree introduced by Laval in '98. And so here on the right, you can see 3 examples of growing this random tree in a very simple environment. And this approach gave rise to a lot of different following tree-based approaches. Another type of sampling-based method is the one is the probabilistic roadmap. Sorry. So the left figure here shows you the seminal idea, the seminal paper on the probabilistic roadmap, where the goal is to sample randomly configurations again, and then rather than growing a tree, they are connected in a limited range to form a graph. Notable extension of this method is the PRM star, which is much more densely connected, but this provides a guarantee that the paths we find with PRM star are going to be much closer to the optimal length than the ones with PRM. Another type of planning approaches is to directly derive a roadmap, not from random samples, but from high-level environment features. So this is usually done by exploiting the underlying structure of the sign distance field. And rather than sampling, which is sampling the environment, which is very fast, we spend more processing time on the environment model, to directly extract the roadmap. So here you have an example on the right, which is based on the Hamilton-Jacobi skeleton. And you can see that from the occupancy map, we can actually extract a skeleton, which then gets translated into a graph of edges and intersection. However, this type of approaches is often limited to small environments or geometrically simple environments because they are more computationally expensive than the sampling-based ones. On the exploration side, in the literature, we find mainly 2 types of exploration strategies, either frontiers-driven or information-driven. So the frontiers-driven strategies consider the interesting areas to explore to be the neighboring space between the free space and unknown space in occupancy maps. So you can see here on the left how some frontiers look in a very basic environment where gray represents unknown space and white represents free space. While on the other side, information-driven exploration relies on the information in the sense of channel theory. And so in this sense, the areas of high entropy in a map will be the ones that are of most interest for exploration. So here you can see an example of on the right, of a partially explored map and how the information map would look, even though here we don't have the past data. From these two types of main strategies, we can also, in the literature, we find there more recently a lot of hybrid or more approaches that take into account a bit more different components. So they often combine a search of the frontiers with a sampling-based approach, and then they choose which frontier to go towards with information criteria. So here on the right, I'm showing two examples. The top one is the dual-stage viewpoint planner, which uses locally an RRT to look for frontiers, and then a global graph to relocalize when there are no local frontiers anymore. And in the bottom, it's a similar approach which samples future paths in the environment and sorts them based on information content. So now let's dive a bit more into it and start with the planning aspects. A tool that I used a lot during my work and which you will see appearing quite often after is the bubbles of free space, which were introduced by Quinlan in 1993 for path optimization purposes. So the definition of a bubble is of a bubble centered on a configuration Q0 is the set of configurations which are closer to Q0 than the sign distance field value at Q0. So you can see here on the right how it looks like in a simple environment when Q0 moves. The bubble is adapting its size to fit without intersecting any obstacle. And so here, since we are working in a 2D or 3D workspace, the bubble becomes either a disk or a sphere. So from these bubbles, our goal in the next part is to construct roadmaps from such bubbles using the bubbles as vertices in the roadmap. And so if I take an example here in the top right of a simple set of bubbles which are maybe randomly distributed in the environment, we can define an edge validity condition to check if they can be connected in the graph or not. And so this first validity condition here is simply an overlap condition. If two bubbles overlap, we know that there is a feasible path between their centers. And so it just comes down to summing the radii and checking if the sum of the radii is higher than the distance between the centers of the bubbles. But I'm going to show it on my screen. But you can see here that these two edges here are maybe, depending on the noise in the environment, depending on the noise that we have when we measure the radius of the bubbles, maybe they are not exactly correct because they are near tangent, and so they could be disconnected quite easily. So to handle this case, we add an additional constraint to the edge condition, and we take the barycenter of the overlap area between two bubbles, and we check again at this point if a radius bubble can be put with a safety radius that we define in the vet. Another good property of the bubbles for path planning is that they are, if we have a path defined by a list of bubbles, Quinlan in his PhD work in '94 showed that we can define these spline control points directly from the bubble centers and radii, and the B-spline that is defined this way can be shown to remain always inside the bubbles, and so to remain safe with respect to distance, safety distance. It remains safe. Sorry. So to construct such roadmaps from bubbles, we proposed the first approach in 22. Which so the main idea behind this one is to use it's a sampling-based approach. We sample bubbles in the environment randomly, but once we have a graph, we start to have a graph. We use the current bubbles which are in the graph to bias the distribution of future samples. So the idea here is that as we we prevent the future samples to be put inside the existing bubbles, the graph should grow towards uncovered space incrementally. So here on the left, you can see a few successive steps of adding new bubbles to the graph randomly. And on the right, you can see an example for a pass in a bug trap-like environment, how the graph is able to grow up to the target and to provide finally a good pass. However, with this approach, we still have a lot of limits, which are pretty standard in the path planning algorithms, but even though we showed that we improved on these issues, they are still present. It's very difficult to discover narrow passages. We can spend a lot of sampling time without finding these passages. The fact that we use distance-based bubbles introduces a high computational overhead, because here we were still working with occupancy maps mostly. And so the distances for the bubbles had to be computed on the fly, which is not an efficient way of doing it. And finally, it's still a probabilistic method. And so depending on the environment we are working with, we have to adapt the tuning so that the method still behaves. So in 2023, we developed a new method, which this time tries to still construct a graph of bubbles, but we want to improve the location of the bubbles by exploiting the structure of the environment in the form of the skeleton. So to extract the skeleton, we start from the sign distance field. You can see it here on the left. So the gradient of the sign distance field is not displayed here, but we can compute its flux, which is the second figure here. And once we have the flux, we can threshold the flux to get the third subfigure. And here you start to see the shape of the skeleton. It's still not directly usable in this form. And so we've seen it to obtain the final skeleton here on the right. However, this skeleton here is still in the form of it's a 2D image, basically a map, and so it's not very easy to use directly for planning. So that's why we reintroduce the bubbles. And so the idea here is that we have our skeleton, and we are going to sample the bubbles on it in a radius descending order, so that we put the biggest bubbles first. And once all the bubbles are sampled on the skeleton, and once there are no skeleton points left to sample, we can apply our edge condition described before to link all the bubbles together and obtain finally the roadmap. And so here we have a deterministic construction process, which gives us a roadmap which correctly approximates the topology of the environment. I think something we did more recently is to show that this approach with the extracting the skeleton and putting sampling bubbles on the skeleton can be extended to 3D with few modifications. Here on the left, you can see a side-to-side comparison with the same sensor data, either integrated in 2D or in 3D, how the skeleton looks different in 2D and 3D, and how the bubbles also are different. Note that there is no direct equivalence. We cannot go from the 2D bubbles to the 3D bubbles, or the other way around, because in the end, the 2D and 3D space are not directly comparable. On the right, you have some more examples in very simple environments. So the bottom is a simulation environment, and the top is a mock environment with some narrow features to show that we are able to plan paths through very narrow passages, even in 3D. To evaluate experimentally this method, we initially focused on 2D environments, because at the time of writing the paper, we didn't yet have the 3D extension. So we use a varied suite of environments, from very geometrically simple one, but with narrow passages, to a complete maze of not high dimension, but big maze. Here are a few examples in two environments that I showed before of how our roadmap looks and what kind of path it runs. So for each figure, on the left you have the edges of the roadmap, and on the right you have a list of paths going to all reachable bubbles from a single source point. and they are colored here by length. And so to compare this method with state of the art, we chose to consider two different baselines. So we consider the PRM star, which, as I briefly discussed in the intro, gives us a good proxy for the optimal length path. And then one of the interesting properties we wanted to look at is sparsity, because sparsity of the graph decreases the query times once the roadmap is constructed. And so we are using as a baseline the IRS planner, which is a planner which uses the PRM star as the base and then degrades the quality of the edges up to a certain point to improve sparsity, but it also degrades the path quality, of course. And so here in the bottom right, you can see on the left in the x-axis you have the number of vertices in the roadmap. So in our case, it's a single point because the construction is deterministic, but others, as we increase the number of vertices, the quality of the roadmap should increase. And on the right, it's the sparsity of the obtained roadmaps aggregated on all the environments. And here the sparsity is defined as the ratio of number of edges to number of vertices. So a lower sparsity means a sparser graph, actually. And we can see in both figures that our method is both able to reach more position in the environment than the baselines with fewer vertices inside it. And it's also much sparser for higher reachability than the baselines. From this simple roadmap, we can also directly extend to frontiers exploration, first frontiers exploration method. So here the frontiers are characterized using the bubbles, and the setup is so the Pioneer robot equipped with a 2D LiDAR to manage the occupancy map, and a fixed RGB camera, which is used only for 3D acquisition here, but not for the planning directly. I'm first going to show the simulated results. So here we are in the CMU indoors environment, and you can see that the green trajectory is the past trajectory of the robot, and the red path is the current plan. And you can see that it plans towards successively towards the frontiers of the environment, and it's quite so. One of the advantages of this approach is that it's quite decided in where to go. It's not doing a lot of backtracking unless it's stuck in a dead end. So yeah, I'm letting it do its thing until the end, but shouldn't be much longer now. Perfect. We have the equivalent in a real environment, so it's a bit more difficult to show side to side what's happening here, but you can see that we managed to deploy the same strategy on a real robot in the lab. Here it's exploring the rainbow corridor that many of you know well. But yeah, it's working both in simulation and in a real environment. Yeah, just to show a bit more in details the results. On the right, you have the exploration trajectories in all the testing environments we tried. And on the left, you have the data acquired by the RGB camera, and so the point clouds which are reconstructed at the end of exploration. It's not easy to see here, but we still have a lot of limits with this method. So the planning is fully LiDAR based, and the RGB camera is fixed. So we don't take into account at all the camera sensing constraints, mainly the field of view. And so the reconstruction is incomplete. We are missing, we have a complete floor plan thanks to the frontiers exploration, but we are lacking a lot of 3D data and texture data that we didn't get from the camera. Also, another issue with this frontier strategy is that it's kind of a minimal effort, because when we observe a frontier, it disappears by definition. And we don't have any incentive with this planning approach to revisit an area that we saw already. So that's why we need a new approach. So First, to introduce it briefly, I'm presenting the new setup that we will use with this approach. Here we want to control the camera view direction to improve the acquisition of 3D data. Problem is, if we keep using a fixed camera, then we have a very strong coupling with the base. And since we are using a differential drive base, it's quite complicated to control the camera view while following a precise navigation path. So that's why we developed a pan tilt actuation for the RGBD camera, even though in the actual experiments, only the pan angle was used because we are in a 2D setup. We also removed the LiDAR to simplify the system integration and to show that this way we prove that it's feasible to actually do exploration only with a camera, even though here it's an RGBD one, so it helps acquiring the data. So the idea of this new strategy is to do it in 2 stages. The first stage is going to consist in selecting the proper navigation path. And once we select a good navigation path, then we optimize the sensor view along this path. And to do so, we first have a block here of map processing, which is going to take the sign distance field we get from the SLAM and to produce an information map, which will inform the optimization blocks. So first, we need to do a bit of work on modeling the directional sensor to take into account the camera constraints. First question we want to answer is want to characterize if 2 points are able to see each other in the environment. And so this is a simple line of sight check. But more importantly, we want to characterize if the sensor is able to look at a given point in the environment. And here, so we still have the line of sight check between the sensor and the target, but we also want to ensure that the target is inside the field of view and the range limits of the sensor. So to perform the line of sight checks, it's a ray casting problem, so we want to cast rays in the environment. And the standard approach to do this is to march the ray with a fixed step in an occupancy map, for example. But this is not very efficient, and we have a sign distance field here. So we can improve this method to use ray marching, or it's also called sphere tracing in the graphic community. So here the idea is that we can step directly at the distance, at the value of the distance where we are currently. And so the hit point here, so you can see on the left here how one ray is marched and how this translates to the parallel simulation of many rays. And we denote the hit point as H of P and V, where P is the view position and V is the view direction. So now that we have this ray marching in place, we can finally go on to build the information map, and we do it based on visibility condition. So first we characterize for a given position in the environment, we want to characterize how well it has been observed in the past by the sensor. So we call this quantity CS of position P and of a past trajectory pi. So for all the discrete, so for the past sensor poses, sorry, position and view direction in the past, what we do is that we just count the sensor visibility condition that we described before to obtain a map of counting how much each grid in the map was observed by the sensor in the past. To translate this count to actually an information map, we pass the CS quantity into a decaying exponential with parameter ni, which characterizes the typical number of observations that we can observe a single cell until we get all information that it contains. And you can see here on the right how this kind of information map looks. So on the right for a 3D environment and on the left for a 2D environment as the past trajectory progresses. However, so this quantity IS of P and pi only characterizes the information content at P and not seen from P, which is what we want to actually get to plan for a sensor view. And so we define a derived quantity, which is IS dir, which is the directional information. And to translate from the point P to the directional information is a translation of the information map using the array marching operator. So we march array from P and we compute the information at the endpoint of the array. So now that we have some information maps, we can use them for to define the navigation reward and the view sensor reward, which are going to be used in the optimization problem. So here I'm starting with the navigation one. So to define a reward for navigation, we want to take into account all view directions, because at navigation, at this first planning step, we don't know yet which way we are going to look in when we navigate. And so we just define the reward for a given pose in the environment as here on the left, R-info of P, which is just discretizing the view workspace and summing in all directions the information that we would get. And from this reward, we can define our optimization problem for the navigation step. So we want to minimize the travel costs of the robot while maximizing the information it gets. So that's why we have this optimization cost defined as a ratio of travel costs and info reward. We also have a minimal reward constraint to ensure that the path we will follow will bring us a minimal amount of information. And the set of candidate paths that we optimize on is provided directly by the skeleton roadmap. So you can see on the top here how it looks. So on the left, I'm illustrating how the reward of information looks for the different bubbles. And on the right, you can see the different paths that the roadmap provides as candidates. The ones in red are the ones which don't satisfy the minimal reward constraints, and the other ones are colored by their score in terms of information. So now we have a way to compute future navigation paths, but we want to define the sensor trajectory, the sensor view trajectory along this path. So this time we want to take the field of view into account, and we also want to penalize close view observation, in the sense that if the camera is looking directly at the wall from a close perspective, it's going to induce occlusions for the rest of the scene, and it's also inducing a loss of visual features, which can be a problem in the case of visual stunts, for example. So here to compute the reward for the view direction, we split it into two components. One is the view information reward, and the other is the view distance penalty. And the view information reward is constituted, so to take into account the field of view, we do it with a Gaussian. So for a given direction, we also take into account the neighboring rays in a Gaussian fashion. And we multiply it by the directional information as defined before. So you can see on the map here, on the left, we have a mock information map where the white space is free, gray space is unknown, and so has an information of 1, and black space is obstacles. So what you can see is that so the red point here is from where we consider the robot to be viewing the scene, and we want to characterize which view direction is the most interesting to look at. So here we have the length of the rays. The rays are colorized by length, and so this informs the view distance penalty. And on the right, it's the rays colored by directional information. And so you can see that the only rays which are going to be informative is the one which hits inside these gray areas. And so when we combine these two proxies, we get the angular score in the bottom, which gives us for each view angle how informative it's going to be to look at this direction. Another example, we can do the same here on the right end of the environment. So here we can see that this time in terms of view distance, the better direction is towards the left. And we have two lobes of information in the information view, because this time we have two very different directions to look at to obtain information. Then we can aggregate this view reward along a complete path, which, as you can see here, this is what it looks like when we when we split the path in multiple waypoints and stack these view scores along the path. So what we obtain is a map which is in the coordinates are the time along the path. I mean, not the time, the parameter t along the path, and the view angle. And we know at any point on the path which is going to be the most interesting view angle, which enables us to optimize the sensor view. As shown here. So here we start with the same path as before, where all the camera views are towards the right of the environment. And you can see, so we optimize the sensor view by gradient descent. The gradient is directly computed in this cost map by finite differences, and then we descend the gradient standardly until the optimization converges. And we can also do this in 3D environments, as you can see here. So the problem with optimizing the sensor view is that it's going to induce information dilution. If we have a very long path in the environment and that most of it is already known, then the gradient descent is going to have trouble finding the correct position on the path where it should focus the optimization efforts. And we can also, if we optimize for information only and that the path is planned towards an unknown area, it can happen that we optimize the view for information, but that we forget to look at the unknown space. And so it poses the risk of enforcing collisions with unseen obstacles. So to solve these issues, we introduce a new notion, which is path observability for the sensor S. The idea here is simply that a path gamma is observable for the sensor if we can find one view direction at the start of the path, which allows to observe all of the paths with taking into account the sensor constraints. And so with this notion of observability, we can, from the global path we compute at the navigation planning step, we can construct a path subdivision where each subpath is going to be observable in the sense I defined just before, and so that the view optimization can be applied only per subpath. And since we have we have for each subpath a constraint view range which comes from the for each subpath, we have a constraint view range which tells us, depending on the field of view of the sensor, the right and the left extreme limits angles of the camera view, which is illustrated here in the figure with hatched areas and full areas. And you can see, so for different field of view constraints and range constraint of the sensor, how the path subdivision is changed. So to summarize a bit this exploration strategy, so the first step is to construct an information map based on the path sensor trajectory and on the sensor constraints. From this information map, we can first compute a global navigation path and subdivide it to ensure that each subpath is observable. And then for each observable subpath, we can compute this cost map, which gives us the view information, and we can optimize the sensor view along the navigation path we planned. So for the experimental evaluation of this method, I'm focusing on the simulation, on these simulation environments here. So two of them are custom, and one is a very standard. The power plant is a very standard environment in the testing for mobile robotics. So the two on the left have been tested in 2D, and on the right we tested the two in 3D to compare for the middle one, the 2D and the 3D method in the same environment. But here I'm going to focus on the power plant. So here in the bottom left, you have the exploration trajectory achieved with our strategy. And on the right, you have so the other baselines. We evaluated our method in ablation study style with one baseline, which is the autonomous exploration planner, complemented by a skeleton roadmap rather than RRT. And so orange is our method, but without any view optimization, and green is our method, but without subdividing the path, so that, as you can see, it fades quite fast due to having optimized the camera view without taking into account the obstacles, and so it encountered an unforeseen collision, which made it fail. In terms of the more measurable progress of the exploration, here it's so we take as a proxy for the data acquired the mapped volume, which is mapped depending on the length traveled by the agent. And so we see that our method is able to explore faster than all the other baselines for the I'm also demonstrating briefly a real case. We did experiments in 3 real environments. So with this setup that you already saw. And here it's in the cafeteria at Groupe Créative. So you can see on the left the bird's eye view of the reconstructed environment, and on the right is the pose of the sensor reprojected in the reconstructed point cloud. So as you know, with real experiments, we have a lot more noise, a lot more reflections in the environment, which makes it a bit difficult to obtain a good quality of reconstruction, but still it shows that the agent is able to explore autonomously in this environment. Finally, to conclude, I'm going to do a brief recap of my contributions. So in terms of planning, I exploited mainly free space bubbles to plan better path. So the first approach was based on the bias sampling approach, which was probabilistic, and it provided some good results, but was still not enough to achieve the quality of path we wanted. So we then moved on to implement a skeleton-based deterministic approach this time, which we showed to improve performance in a lot of different metrics, so coverage, sparsity, also correct time, and which we demonstrated in various environments. And then we used this roadmap to progress towards autonomous exploration and reconstruction. First, by exploring the frontiers-driven strategies directly on the bubbles roadmaps, which gives a good exploration behavior, but is not insufficient to make sure that the reconstruction is going to be of good quality. And so that's why we went on to develop directional information rewards to take into account the constraints induced by directional sensors such as a camera. And finally, we extended these new information rewards, which are directional, to an information-driven strategy. And here we adopted a coupling approach to plan first the navigation, set the navigation path, and then optimize the sensor view along this path without compromising safety, of course. I'm also briefly mentioning the technical contributions of this work. We integrated various sensor setups, LiDAR only, and then LiDAR and RGB cam, and then the pan-tilt camera. And all of the code that I produced during this PhD is open source on my GitHub page. You can find it easily. However, we still have a few limits that we encountered in this work. So the first one is the mapping backend. To ensure robustness of the experiments, I used mapping backends which are a bit dated now. I mean, they are not the most recent state of the art. And so particularly in real experiments, it was difficult to balance the integration time of the mapping algorithms with the fact that we need to construct the map on the fly. Also, the robot representation is still very simple. We are in this work, we always consider the robot to be an inflated point, so either a disk or a sphere in 3D, which was okay for our robot, but it's not for legged robots or for more complex environments. It could be limiting. And finally, the main limit I found in this work is that evaluating the performance of an exploration method is not straightforward. Even to evaluate the evaluation performance of a human would be difficult to rate how well he did. So for a robot, it's even harder. And so what I found to be the easiest way is to really compare methods which are close to one another, and this way we are sure that at least we have some comparable elements between them. Finally, for some brief perspectives, so the first one would be, of course, to improve the performance of the geometric mapping aspects. As I was mentioning, it's the main limitation for now to run faster experiments. We could also include in the exploration semantic data. Nowadays, with the advent of deep learning methods, it's becoming easier and easier to obtain semantic information from a camera sensor. And so with the final framework I presented, if we had semantic data, it could be also implemented in this kind of directional information maps. And finally, something a bit closer to what the team here in Rainbow is doing. These planning methods could be extended potentially to multi-robot systems without too many adaptations to the theoretical background. I mean, we still need to take into account intercollisions between the robots, but that would be, I think, the main issue. And thank you for your attention.
Thank you very much for your presentation. So we will start with the reviewer of your report, and I will give let Professor Lavallée do the first comments and remarks.
All right, thank you very much. Thank you for the good presentation. I very much enjoyed reading your thesis, and as I wrote in my report, I thought it was nicely written, and you make good contributions that nicely integrates concerns from both sort of online, real-time, sensor-based exploration together with planning algorithms, and I thought it was nicely done. And it's nice that you demonstrated that both in simulation and in practice, which is always an additional headache. I also thought that today your presentation was very good and very clear, and I appreciate that you're doing it in English, which is also an extra hassle on top of everything else. So, so thank you very much for that. So I do have some questions, of course, as is my role here. Do you have your thesis available, or is it
Not?
Okay, well, I can tell you what's in it, and maybe you remember.
I have it on the.
Oh, okay. Yeah, no, it's okay. So in the very first line, so page 5, you open by saying you introduce us to field robotics. You say, this is one of the main axes of robotics research, field robotics, taking robots out of the lab. And as I start reading the context of it, I start to think, oh, this is going to be about robots exploring out in the woods and this kind of thing. So what it seems like you set the wrong kind of context for the work, or I'm kind of confused by your motivation for doing that. So I just want you to kind of explain.
Yes, so so I think it's more of an issue of how I wrote the context in the manuscript rather than because the context of the work is pretty clear. It's
exactly. No, I'm just commenting on the manuscript. Yeah, the presentation is fine, but you open your thesis presenting a context, but then your presentation here and the works that you give don't seem to match. So, or maybe you argue that they do. I just want to know your thinking.
I think that they would, but not directly. I think that the exploration indoors and outdoors are kind of related. As I showed, the last method we presented is able to do either indoors or outdoors exploration. So there is a link between both, but definitely for the application context of this work, it's focusing on the indoors setups with ground robots. Yeah.
Do you have some dreams or aspirations of maybe extending these things to outdoor?
Yes.
I see. So we can consider the context like that. I have only a couple of references like this, but on page 32, you when you introduce configuration space, I'm very much accustomed, and for a lot of my questions and comments, you can imagine as if I'm a time traveler from the late 1990s. So I have a lot of perspective, maybe from that. It's not too far, pretty close to truth, I guess. And so I'm very much accustomed to configuration space being some higher dimensional space that corresponds directly to the degrees of freedom of the robot, and the workspace is 2D or 3D, and that very much corresponds to the geometry that we have geometric models defined exactly in that space. So, but it looks, I don't know if you're confusing them, or as I go through the thesis, I see a lot of talk of configuration, but do you just mean points in the workspace?
Yeah.
So why use the term, I guess?
I was taught with the configuration spaces, and then Yeah, I kind of never.
It's not mathematically incorrect, but it just contradicts the kind of naming conventions that I'm accustomed to. So I just wondered.
Yeah, true. In my work, I mostly collide both terms to describe the same space, which is my 2D or 3D workspace. Actually.
Okay. So I'm always, again, when I was a graduate student, I learned, for example, from Jean-Claude Latombe's book, which was in basic note form at the time that it came out in 1991 or so, but there was a very kind of large distinction. And Tomás Lozano Perez, before that, a decade before, it kind of unified the field of motion planning around configuration space notions so that we could develop planners to work in almost anything. So that separation between those is very important. It's okay that they're kind of the same thing for yours, but it was kind of unclear to me.
Because I also, I started, I learned the configuration spaces. I mean, I also learned planning with the RT and configuration spaces for manipulators.
Okay.
And then since so that was like 5-6 years ago.
I see. So it's very natural for you,
and then I moved on to work here on the PhD, and so I didn't do a lot of mathematical work in the beginning. So I started naming things just how they felt, and so I did the collusion between the two.
Yeah, I mean, it's at the end of the day, I can read it and it's clear enough, but I just wonder.
I will try to make it clear, maybe in the.
And then this is very related, I guess, with regard to, say, RRTs and probabilistic roadmaps and these things. The design of those methods was for so-called high-dimensional problems, like 6-dimensional configuration space was considered kind of high-dimensional in 1995. And maybe they go higher, hundreds or thousands. It's fine nowadays, but I'm kind of in developing the RRT myself. I was motivated by high dimensional spaces because I felt like in 2 and 3D we already have a bunch of stuff that works, like A star, D star, all kinds of things that work on grids. And when you have polygonal representations or polyhedral representations, you have computational geometry methods that are ridiculously fast. Very clean, very beautiful and exact. So sampling based planning, I'm surprised. I see it used quite a bit, not only in your own work, but I'm surprised to see it. What is the motivation for this kind of approach in low dimensions over because like you're missing the corridors, for example, as you were saying. It's like, well, of course you're missing them, but you also have direct access to them. And in regular motion planning in 6-dimensional space, you don't have exact representations unless you've done a bunch of crazy computational real algebraic geometry to find exactly where they're at. But in this problem, you have a grid or some kind of direct access to it. So why does that seem like the right family to even look at?
I think the first motivation was the fact that we don't know in advance the size of the environment, so it can grow up to a very large size, and then some computational, like the A star, degrades, the performance degrades quite fast as the environment grows in size. And similarly for, I tried at some point to do from the occupancy map to extract some geometric primitives such as segments.
Yeah,
because then it's much easier to do.
Yeah, that's one of my next questions, in fact. So that's great. No, that's good. Why not do that?
I tried it. So it's the main problem was the sensor noise, because I mean, sensor noise or map noise, depending the way you see it. But as the map provided by the SLAM integrates more and more sensor data, sometimes we'll have walls which are not perfectly straight. So fitting a segment is not going to exactly, all the segment is going to shift in time as the wall is corrected by incoming sensor data.
Okay, so a bunch of jagged polygons and like lots of little edges, garbage everywhere.
The fact of one of the main issues with that was to find doors, like find the openings in the walls, because it was very difficult to differentiate between a door and a sparse sensor reading of a faraway wall.
I see. And going back to the 90s, I would say a 100 by 100 grid was, pretty big. What's an example? I don't see a lot of like grid dimension kinds of things in here. So what's an example of oh my gosh, that's a pretty big grid, or what? This is a normal size grid. And
so a normal size grid, I would say is so the normal size I used in my experiments was usually around 200 by 200 pixels. Then the big grids are more towards the 800 by 800 or 1000 by 1000 pixels wide.
Yeah.
And then when you add the third dimension, then that's where it becomes an issue, because a grid of 1000 by 1000 by anything becomes very difficult to query quite fast.
Yeah, but if we stay in 2D, then it seems like these D star algorithms and things like that ought to work really, really fast these days. Is that
Yeah,
right?
I
Did you look at
didn't,
those kind of things? They're like A star, D star?
I didn't. No, I didn't look at them. I mean,
Yeah.
I didn't. I know them, but I didn't compare them with.
Yeah, it's
what I
okay.
know through
Yeah.
also, they have an issue of not being super safe because they are going always to find the shortest path, and so they are going to stick to the walls basically at any corner that they can.
Oh, well, there's the classic trade-off between clearance versus shortest path. Be
Yeah.
careful what you ask for, kind of.
Yeah.
There's always this kind of difficulty. Yeah, that's fair enough. There's beautiful computational geometry-based methods like that generalized Voronoi diagrams and these kinds of things. But I guess if you don't have polygons, then you're going to have to do numerical kinds of things that you've looked at, for example. And so then it fits very well. Like then these sign distance fields and things like that make some kind of sense. So I guess that's reasonable. You mentioned on one of the slides about approximating the topology. It's slide 29, I think.
Yes.
Yeah, and I'm not sure of the culture here, but if I go too long, the president can stop me, I guess, right? So, okay.
It's this one.
In Finland, we go for hours, so yeah. No, just kidding. Sorry, I'm just trying to scare you.
Sometimes lunch will be necessary, but
Oh, no, I don't
we can
keep.
come back after if you want.
Oh, no, okay. Yeah, no, this is very interesting work, so I want to get some questions in. So okay, this is two-dimensional, so I guess, and you made the statement correctly approximates the topology of the environment. So I guess in 2 dimensions, the only kind of topology I could think of is connected components are preserved, and if there's a cycle, then you capture that. But when I see this blue graph here,
Yeah, true.
I see all kinds of extra cycles. So if I had just made a high resolution grid, sorry, and I just made the edges up, down, left, right to your neighbors, would I be able to also argue that that's correctly approximates the topology? It's making all kinds of extra little cycles around every grid point, but it's going to capture every hole if it's a high enough resolution grid. But a topologist might say, it's kind of garbage. You have not really. So have you really? What do you mean by approximating topology?
It was more in the it's more in the overfitting way as you describe it. It's to say that we don't miss any. Also, even in this example, I'm missing a connection in the corridor here, as you can see.
Yeah.
I mean, I'm going to show it on the screen because at the distance we don't see it. But
so no holes are missed somehow.
That's more the goal is to miss no. Since my main limit with the previous one was to find the corridors.
Yeah.
It was really in the sense I approximate correctly the topology because I find for any corridor I can traverse it, and I know that if there is a connection, I will have it also in the roadmap.
I see. That sounds reasonable. I guess phrases like approximating topologies, sound kind of a little fancy, but they might not be so meaningful. If I were to go over to ENS and bring a topologist over here and say, "Do you think this is like something?" They'd be like, probably not. So just, but I know that these kind of terms are used a lot in robotics and such. So, but I'm going to be extra picky and just sort of say that I'm not convinced that that's approximating topology, but I understand what you mean by capturing the holes, kind of identifying the holes and maybe making a few more artificial holes because there's more loops there that are kind of unnecessary. So that seems unreasonable. You mentioned that the sampling based planning methods are probabilistic. And that was one of the shortcomings, but I just wanted to point out at some point we renamed the field from randomized path planning to sampling based path planning precisely because we can use deterministic sampling methods. So if you use any dense sequence of samples instead of random, you get a deterministic method. So have you thought about that, or is there really something inherently like it's easy to make the probabilistic part go away, but maybe the methods are problematic for some other reason? I just want to.
So I'd say the part where I was referring to the probabilistic issue was I think it's because the probabilistic methods I tried, so the sampling based method as well, they were more limited by tuning factors at some points because you need to tune the sampling density or the length of the edges you want to connect, or there are some parameters to tune. And I found that it was harder for me to tune it was hard to tune to find a set of parameters for one sampling based method which would work for a variety of environments, let's say.
Like radius connection for probabilistic roadmap or things like that. I think like for the RRT, we tried to eliminate parameters. There's a metric but this is a simple 2D or 3D geometry. So the metric is just Euclidean distance. So I'm not aware of parameters otherwise in like say RRT Connect or something. So if you just have a uniform sampling density, uniform deterministic or probabilistic uniform sequence that's dense in the space that you're sampling, but I'm not aware of parameters for that. Like,
No, for DRT, the main issue definitely was the corridors. Like to find the narrow spaces was very difficult because the sampling, whatever sampling, if you sample too dense, then you're going to find the corridor that's going to be.
Yeah, that's exactly right. And we can't find these corridors in high dimensional configuration spaces, or it's very challenging. You have a low dimensional problem, so you can find them, but you have to do that kind of grid propagation of waves or search or whatever, which you've ultimately done anyway. So I think you figured that out and went the right way. That sounds very good. And one last question. If you're going to put like a Dubin's car in the environment, so that you don't have instead of a unicycle model like you consider, if you have a bounded curvature constraint or something, do you have any idea what to do with that?
Yeah, that was a question I had also in one of the reviews of the skeleton roadmap paper.
Mm-hmm.
And so it's
it wasn't my review, so
but basically the as you can see the path, they are still so because we use the B-spline smoothing defined by the radii, the centers and the radii of the bubbles. So we actually have curved paths, like they are not we never have zero radius terms, but and so that was my answer also at the time. I don't know how to characterize the minimal radius term we have.
Yeah, I guess if you had like if you were trying to design a vehicle that could go through it, or you want to make it as good as possible for as many vehicles as possible, you could try to reduce the maximum curvature through your choice of spline parameters.
Yeah, and I'm pretty sure that there should be a way to check for a given list of bubbles what the maximum curvature is going to be by applying this spline smoothing. But I didn't do this work yet.
Okay. Yeah, well, thank you very much. I'm satisfied. I hand it back.
Thank you, Professor Lavallée. So now we will switch to the other reviewer, Professor Jensfeld from KTH.
All right. So first of all, thanks for inviting me. I also found it very interesting to read. Exploration is something I'm very, very interested in. Like Steve said, it was nice to see a mix of simulation and real-world experiments. That's something that is not so frequent in exploration. I think a lot of people stick to simulation. I have to confess that we also do that sometimes. It was also nice to see both 2D and 3D. All right. So my first question is also on the first page. So you say that the robot doesn't have any prior knowledge at the start of the exploration. But I would argue that you have prior information. You even your entire and like your development of your methods was sort of inspired by the fact that you had problems sampling in corridors and narrow spaces. So I think you do have some prior information. Could you imagine more prior information? I think we do have more information. Could you think of other things you could make use of that you do have? Even if I'm not saying that you have seen the environment before, but I think you have seen environments possibly before.
Yeah, if we are focusing on the indoor space, then that was also one of the inspirations for trying to fit segments on the walls or to fit. Yeah, it was the main thing I tried. But definitely, when we are indoors, we can expect many more flat surfaces, openings of typical size for doors and windows and stuff like that. So,
Right.
and I think this is something that is maybe it was mentioned in this slide. I'm not sure, but there is a recent SLAM method called the situational graph, which is a hierarchical way of organizing so that the base layer is the geometrical data, but then they try to fit some planes and some so from the planes they have a list of planes that they also use as features in the post graph, and then they characterize the planes as being either part of walls, of rooms, of corridors, and so. But it comes then more to, so I'm pretty sure there is more information to be exploited, like more prior information to be exploited. But then it asks the question of which categories, I mean, you need to start categorizing some features, and so to detect them correctly in the environment. And so it's, I mean, I don't see a purely geometrical way yet of exploiting additional information, let's say.
Right. But like if I'm as a human, if I walk into an office and I see that the office has a window facing outside, that would be a very strong cue for me to say that if I walk into an office next to it, I would expect that there would be a window there as well, and that the wall that has the window is an outer wall, and that says something about the large scale structure of the environment, I think. I mean, you would expect that wall to continue, for example. I also think if you go into an office and you see two walls, you don't see that they actually meet, but I mean, if you have seen enough environments before, you could probably guess that they will meet there, and yeah, those kind of things. So it doesn't have to be just like planes and things, but can say something about the large scale structure of a building, for example, I think. All right. So maybe a question about sparsity. So like that's one of the things you're trying to achieve, like finding good ways to sample and not have so many vertices. So when is how do you trade sparsity versus maybe not coverage, but like when the vertices get sparse, if you use those vertices to create paths in the environment, you may not get the optimal path because you don't have any vertices there where they might be needed. So how do you make that trade-off?
So in the first method, I was dealing with the trade-off in so it was probabilistic. So it was the density was, I mean, yeah, actually with the fact that we use bubbles, it's kind of this density of the samples is affected by the fact that we actually use bubbles, because when you put a bubble somewhere, it's going to create an exclusion zone around it.
Yeah, exactly.
In which there are no more samples, and so that's why the placement of the bubbles is kind of the critical aspect for this method, is that we want to place the bubbles somewhere where they are going to not decrease the path quality if a path goes through them, let's say.
Right. So if you take the upper right image here, you have this very large bubble in where the two corridors meet.
Yep.
And then you have only one vertex in that quite large region. Yeah, exactly. So, I mean, that means a path coming from below there, at least without path optimization, the robot would go up into the center of the room and then go down if it wanted to go to the left.
Yeah. So this can be, I mean, this could be, I think this is better to mitigate at the post-processing step of the path which is planned. This could be mitigated by cutting, either not going through the center of the bubble, but going through a chord. Then if we use the bottom chord, for example, we can shorten the path. This is kind of already taken into account up to some limit with the fact that we use the B-spline smoothing.
Right.
It's actually going to not go through the center, but to do kind of a curved path from here to here. Because the spline is going to kind of get away from the center.
Right. And again, like number of vertices, is it mainly generating them that is costly, or is it using them when you plan? So you have to, like in at least the first method, you have to recalculate them. So I guess having more vertices is expensive.
Yeah, in the first method, definitely,
Yeah.
it was computing the vertices was super costly because I had to do distance queries on each new sampling, and so it was very costly to generate them, and then using them was similar as for the other methods. But here now that so in the second one with the skeleton roadmap, since the base map is a sign distance field, we already have the info for any configuration. We know which is going to be the distance, and so here generating the vertices is not that costly. I mean, it's the same as for the other methods, and also exploiting them is since they are since the graph is sparser, they are less costly to exploit in a sense.
Right. So when you update, especially in the first method, but also in the second, how do you determine which, like in the first method, it sounds like you recalculate everything, even though unless you have a perfectly open space, your SLAM update is often, at least if you only do mapping and not actually SLAM, it's only going to be a local part of the map that is changing.
Yes.
So did you exploit that somehow, or because otherwise it grows very expensive when the environment gets large?
So in the first method, I didn't. I did exploit it by checking which bubbles had to be recomputed or not. So I was only eliminated. So between two map updates, if some bubbles were still valid, I would keep them in the graph and only.
How did you decide? That's what I didn't quite understand from the thesis. Maybe I didn't read carefully enough. But how did you determine?
It's brute force search on the graph, basically.
And checking what? Like being outside the field of view of the sensor, or?
I know it's.
I guess there's some way to
mean.
eliminate the check at all. I mean, I would almost expect that.
So no, I don't eliminate any checks based on the localization of the robot in the map.
Okay.
And I'm only exploiting the difference between successive maps, let's say.
All right. Okay. Because I think you could probably exploit the fact that vertices that are far away from your sensors will not change. If you could argue then if I define my vertices in a global coordinate system and I have a SLAM map that is sort of moving around, then well, everything will change. And then I think you could maybe do something like attaching your vertices to a post graph or something, and then the bubbles or the vertices would actually change with the map, and then maybe you could almost get away without updating them also when they're outside the field of view of the sensor.
Yes.
Okay. Yeah, sorry.
No, one thought about this is that even though, I mean, it could be doable for very far away vertices, but for the ones which are at mid-range, let's say, with occlusions and how the environment is shaped, it can be difficult to determine if they are going to be affected or not by next measurements, let's say.
Okay. Let's see. I think next one was on page 34. I think if I understand it right, when you decide, like when you do the planning and you decide which, like you are somewhere, you're not exactly at the vertex. Sorry, I'm talking about in the thesis. You're not exactly at the vertex. That's a standard problem. You need somehow to connect to a vertex in the graph. And in my experience, connecting to the closest one may not be the best one to connect to. It could be that a slightly further away vertex actually leads you to a closer or a shorter path. Did I get it right that you connect to the closest and then continue? So do you have any thoughts on that?
I didn't explore, I thought of it, but I didn't explore other options. I think it was pretty rare in the end that I was inside the range of multiple bubbles.
Okay, right.
So
okay, so maybe sparsity saves you here, but that...
yeah.
Okay. Because otherwise you could imagine you are somewhere, there is a short path in one direction, and then there's a very long one in the other direction. You happen to be slightly closer to the vertex that leads you onto this long path.
Yeah, that would be a failure. That could happen definitely.
Yeah. Okay. Let's see. Yes, you have this safety cost, and you define it as the average distance between the path and the obstacle. That seems quite doesn't seem super safe. Like you could have something which is 1 micron away from an obstacle. That would be bad. But if you average over all of the distances, you might almost not see that in the overall value that you calculate.
Yeah, true. I think this was the safety cost for the evaluation of the first one. Am I right?
Yeah. It's on page 45, so maybe it's the first method.
Yeah.
Yeah.
Yeah, so it was yes.
Would it make a big difference if you just took the minimum distance or something instead?
I think maybe I tried at some point to take the minimal, but then you measure only the quality of the path. That's why I changed to an average. It's because you measure the quality of the path only at the worst spot of the path.
Right.
And so to compare the methods, in general, it didn't give a very good intuition of
Okay, I see.
which ones are safest on average, let's say. But
Right.
definitely, I think so since we are using bubbles, they are supposed to be safer than just actually since here it's they are sampled as well. Taking the minimum, I think, would make all the baselines kind of equivalent because it's random how close they are going to be to the worst part of the path, let's say.
Right. Okay, now I move to page 76, and this is where you talk about you're you're searching for candidates to explore, and then you talk about how you select your parameters. So you have this D search parameter, which is between 10 and 50 meters, and then you have some alpha parameter, which you usually pick between 0.1 and 0.33, you say. So
Yep.
First question, how sensitive is your method to the selection of these parameters? Is it something you need to, like, you walk around in the environment and say, yeah, this is a 0.2 environment, or it doesn't matter so much?
From what I remember, it didn't matter that much. I tried, I used here the values that I used in the experiments.
Yeah.
But yeah, it was. The main thing was to favor always the path lengths to try and. That's what I did, right? Yeah. Favoring the path lengths helps not doing a lot of backtracking, so that was the main point. But then, the numerical values in themselves, the search also has an impact because it determines kind of how thorough the search is going to be. Because let's say if I put 1 meter for the D search, it's going to find to search meter after meter. The first frontier it finds, it's going to travel towards it.
Yeah.
If I put 50 meters, it's going to take all frontiers in a 50 meters radius, and so it can have more choice to choose between more informative versus lengths. So that the D search is really not. It sets the behavior, but it's not going to affect the.
Yeah, because you're also extending
quality,
it if you need to. Do you think it would make a huge difference if you just dropped the first term there, the reward for yeah, the expected reward, or just use a binary thing. Is there something or not?
What
So
it
you-
would change is that still I had so since we are using bubbles and they are so in this method they were I mean, sorry, we had a lot of frontiers bubble and some of them are very small.
Yep.
And so the expected reward for the very small bubbles goes down because we are not going to discover a lot of information. And so this was kind of the point of this reward, is to help not going to see areas which are just a tiny fraction of new information, let's say.
Right, but if you instead thresholded this and say, okay, this is so little that I don't care, and it's about selecting where to go among the ones where there is something to see, I think you will get very similar results, especially since you have usually very low alpha and you also have a very strong penalty for path length where you divide by the path length.
Yeah, true.
So I think it's very much working on the path length here, which is my experience as well. That's what gives the best results. So, okay. I think I've asked the questions I was most curious about, so I will hand over to the next person.
Thank you.
Thank you very much, Professor Jensfeld. So now we will switch to the next examiner, Dr. Olej Nikova.
Thank you so much, and thanks so much for the excellent presentation. It was a pleasure to read your thesis. It made me really happy to see some of the things I've been thinking about at the back of my head during my thesis really carried to full completion. So wonderful work, and thanks for inviting me here today so I get to enjoy the presentation as well. I'll start with kind of the nitpickiest questions and go forward to the maybe a bit more open-ended discussion about how this can be applied in different scenarios. So the first question I had is about the safety. So in your work, you always use an optimistic map, so you assume unknown space is free until you do the safety checks. Could we take a closer look at how you do the safety checks again, especially with a limited field of view?
So in the slides or in the
Slides is fine, yeah.
so you mean the path subdivision, right?
Yes, exactly. Where you ensure that, yes.
This one?
Mm-hmm. So here, do you ensure that all space that you cover between, like through the trajectory, is actually observed before you go into it? Is that done through? Okay.
So basically, it's that so if we consider only one of the subpaths, we know that there exists view direction in this range, which ensures that we are going to see the full subpath. And so I didn't mention it, I should have, but it actually acts, this range of view acts as a constraint for the optimization of the sensor view trajectory. And so we know that at the start of the subpath, we are going to be looking in a direction which ensures that all of the subpath is observed. And so if one obstacle happens to be there, it will be seen before we navigate.
Okay. So then basically, if you have an ideal sensor that actually works as is written on the data sheet, then you're guaranteed to always be safe. So what happens if I see you use the Azure Connect in the experiments. What if you have something with a texture that's some obstacle that basically has a texture that's not visible to the Azure Connect? Can you somehow, do you have any additional checks later on as you're executing the trajectory to see if space is still unknown?
Not at all. It happened in some experiments that, for example, in the real one I showed at the end, there was a pool table in the cafeteria, which is black wood, that it just fails to be registered in the map. And so in this case, we just, it was more adapting the environment because it's a sensor. I mean, it's using only one sensor and having the sensor being unable to see the obstacle. We didn't have any other way of mitigating this, or we could have done some collision detection on the wheel slippage or on some current, something like that, motor current. I didn't go to this. I assume that we would see all the obstacles, and that would be so no other way of mitigating it.
I mean, you could kind of flip the optimistic and conservative assumption. So while you're executing the trajectory, you could have some check to say, like, if we're about to go into unknown space and it's still unknown, maybe
Yes,
stop.
yeah,
So because you do have the information, and if you have free space, and unknown space that's in your field of view, you can safely assume that you don't want to go in there. But, okay, not glad to hear that you ran into these issues, but kind of confirms my expectations. The second question is about transitioning from 2D to 3D. So for me, during my thesis, this was always the hardest part. In 2D, you can just, algorithm works, great, and then you go to 3D, oh, no, here's the next couple of months gone. So I believe in your thesis, you say that for the SDF, you computed by doing horizontal slices and then combining it into 3D. So is that strictly correct, or have I misunderstood what you're doing? Because from my understanding, if you do the horizontal slices, which is perfectly valid, you then still need to do another pass to kind of rectify the Z directions as well, in case the closest obstacle is in Z.
So I think so I didn't need the slices to extract the skeleton.
Mhm.
So it's true that I'm not considering the flux, the 3D flux. I'm
Mhm.
considering 2D flux of the slices each
Mhm.
time. But I think that practically it works well enough. I never had any issues in the environments I tested, and so I don't know if it's due to the fact that there is not much of a difference. I mean, I could find some environments, some example where indeed applying this would fail.
Mhm.
But I think it's due to the environments I use, which are very
You have a flat floor.
flat floor and not too flat, like they are not themselves near slices, because I tried some. If you take a very how can I say a very flat brick, let's say, then the skeleton inside it is kind of degraded, because it's always close to either the top or the bottom, and so we don't get this nice X shape of the skeleton inside, let's say. So in some limit cases, I think it would be necessary to take into account the full flux in 3D. But for most of the experiments we did, we showed that in the end, not taking it into account is okay. And so it was faster to do it this way.
Okay, and then you don't actually use, but you use the 2D SDF, the 3D SDF value to compute the collisions as well.
Yep.
So I guess in the cases you said where you have kind of a narrow, maybe some kind of horizontal chimney or so, then you would be in trouble if you don't consider the Z-axis for the drone scenario, for example, right? Because then you would, if you just do this, you can overestimate the your actual collision spheres by quite a lot.
I'm not sure I get the question, because
So if you have if your environment is kind of shorter than it is wide,
yep,
and you have the scenario where you're flying a drone, which let's say it's economic in 3D space, then you would be in trouble, because then you'll overestimate kind of the size of the bubble.
Yeah, but no, but the collision checks are always done with the 3D SDF, that's for sure. It's only to extract the skeleton that I'm kind of degrading the definition.
Okay, so you have a full 3D SDF that's
Yep.
computed the normal way. Okay.
Right.
All right, then that makes sense. No further complaints on that. So then kind of continuing on this 2D to 3D part, I'm curious about, especially in the real world experiment where you're constructing a full 3D map and you're driving a 2D robot that must stick to the ground. I understand how this works in 3D with a drone, right? You just don't touch anything, that's fine. I understand how this works in 2D, you also don't touch anything because the only things you see are walls. How did you make this work in this kind of 3D scenario where you can touch stuff, but it can only be the floor?
So in the end, it was only 2D. Like
Okay.
I didn't have the time to do the last experiment, which would have been because I did so in simulation was 3D. So the
Yes, yeah.
as you say,
Mhm.
the drone is 3D and the view was also optimized in 3D, which means the pan and tilt angles were driven at any time.
Mhm.
But in 2D, I only controlled the pan angle because I was considering I have actually an additional slide for that. Sorry. So in the end, the 2D experiments, these are what they look like. So we use really a 2D map,
Mhm.
and the view is only optimized along the pan axis, and so it's as if everything was 2D, and I displayed the 3D point cloud because I have access to it, but it's not all the planning is done in 2D actually.
Okay.
And the last plan was to do a mixed 2D 3D experiment to optimize both pan and tilt angles while we navigate. Also ensure the position of the floor, and then I would probably have just filtered at floor height to get no obstacles from the floor.
So a further question in that exact direction, I think that's the approach most people take, and that makes sense. But let's say we actually take this outside the lab. Let's say you have some kind of robot that's, I don't know, maybe also a little bit tall, or driving through some rough terrain with low-hanging tree branches, for example. Maybe is similar to the scenario where we flew a drone, where you need to, the robot needs to drive on a manifold that's on the ground. The robot needs to not hit things from the front, the sides, or the top. Do you think the bubbles methods that you've developed would be useful for this, and how could you extend them to be able to handle this rough terrain scenario and while still driving on a manifold?
Yeah, that's a difficult question because let me think. So that's kind of what I was trying to say when I showed the slide with the 2D and the 3D models. There is no relationship at all between the 2D and the 3D ones, even in the same environment. And so, yeah, it seems like it wouldn't be a good. I mean, I don't see it straight away how it could be expanded to outdoors, like real outdoors environments, if we need to drive still on the ground, because then maybe with I only think of a projection, but then it's deforming everything. It's not great. So no, I don't see a direct way to extend to it.
So I mean, I think if you kind of separate the driving part and the not hitting things
Yes.
in the environment, then I think you can still use kind of everything you've done for the 3D part of it, like, you know, avoiding low-hanging branches and so on.
Yeah.
But yeah, but I think
For the collision avoidance would be quite nice, but for the ground parts, like the how to drive on the manifold, as you say, there I don't see how they can help directly because they are not made for this kind of weird space.
Okay. All right, and then one kind of final question. So one thing I always think about is, when do you need a global map versus a local map, and when are they useful, and when do you really care about having high resolution, and when do you just need to know where things vaguely are? And to me, the bubbles seem really like a natural way to really compress, especially large maps, where kind of in your current field of view, you really want to know exactly where obstacles are, and then further away, you can just forget the SDF or the occupancy map and so on, and just keep the bubbles to be able to do a global planning. Have you looked into this? Do you have any further thoughts on kind of using this hybrid approach where you forget everything but the local map and keep it as just bubbles?
No, I didn't try it at all, but it's a very good idea. I find. So thank you. Since I was focusing on the exploration completeness, and also I was always driven by the global map the global map has always been my target, like, and my way of evaluating if the method was working correctly or not by the quality of the final map. So I didn't explore at all the side of eliminating the map and only navigating in local space. But for other even for exploration, it would be a good like we don't need actually the full map at exploration time. We only need it at reconstruction time, at post-processing time. So it could be storing the data and only navigating the local space and then doing everything offline once the exploration is done. And I think completion can be partially characterized by the bubbles when we are. I think it could be feasible to say if we're, I mean, to determine if in a local map the bubbles we computed until now are a good approximation or not. And then if we move away from the space, we can keep in mind if the bubbles we saw were a good approximation or not, and if we need to revisit or not. So yeah, would be a need to explore in the future, I guess.
And I think, I mean, I feel like the bubbles are just such a compact representation of so much information about the space. So that's actually very useful for navigation. I think if I were to deploy this on a real system, I'd really want to exploit this the sparsity problem and property and throw everything else away. Okay, and maybe I sneak in just one last little question. So speaking of building up a globally consistent map, which is the goal of all SLAM algorithms, how much issue did you have with drift and localization failures and so on, especially in the real experiments?
So when I was using, so initially in the first experiments, the first real experiments, I was using Artan map as the SLAM, and so when it was working with so with this one, I never had many issues with drift, except in the simulation in the very large. I don't know if I have it here. Yes, in the top right one, the tunnel. I had to do a bit of tuning to make it work for that long, because here the experiment is like something like the trajectory is 6 kilometers long and it took 10 hours to drive it. So, but for 10 hours it stayed strong. But there, yeah, definitely I had some tuning to do, otherwise it was fine. But with when I switched to using box blocks, it's not doing the localization. There I had a lot more issues in the real experiments, because the drift accumulated quite fast after maybe 50 meters of driving. So that's why also you can see here the maps are quite large in terms of the area they cover, but the ones I don't have them, I think, yeah. The other ones, the ones we did in real experiments in the last strategy, they were not as big because of the drift, which at some points lost the robot completely. So yeah, I had a few issues with that I didn't have time to solve. So
Okay, thank you so much. Yeah,
Thank you very much. So we will switch now to the supervisor. And non, moi après.
C'est le président.
Le président le décide. Professeur Marchand.
Okay. So first, I'd like to thank the jury for being there. It's always a pleasure to have so impressive jury. So thank you for being there, for your report and so on. Thibault, it has been a great pleasure to work, to be able to work with you. It was not obvious to advise you on a subject like that, planning, large scale exploration. It's not our research subject, main research subject. So we have to go out of our comfort zone for that. But hopefully, you are bright and a very independent student. And independent is a key word there, hopefully for us. You have good idea, and your idea are clearly not ours. This is yours. And you have also the ability to implement this idea from software to hardware. You also build your own patented system. You don't say delete, but you build it. What I also appreciate is that, as an advisor, is that you work perfectly. It's not always the case. The structure of the paper is always fine. The style is good. You have nothing to do with your paper. This is really a great pleasure, I have to say. Obviously, the 3 years of a PhD are not always a straight line. It has been sometimes difficult because perhaps you were too involved in your work. And that I also want to thank the member of UCIC, Marie Babel and Nicolas Moussard, who a few times told you to step down a little bit, to take some vacation, and you come back better after. And I think I really want to thank them for that. They're not there, but I think it was important. I don't ask you some question, obviously. I don't know what you will do in the future, but I hope you will continue to do some research, and I hope we will see you in robotics conference in the future. So no other question, but thank you for it. Thanks a lot.
Thank you very much. So we will switch now to the next supervisor, Mr. LEHUGER. The floor is yours.
Thank you. It is with great pride I attend this defense today. In fact, this study is part of a project initiated in 2016 by financed by Groupe Créative and encouraged by our management, Raphaël Doyen and Sébastien Guyon. Explore was an ambitious project with modest resources to support such an ambition. However, thanks to your involvement, maybe two, the results have far exceeded our expectation in terms of fame. I think this success is a testament to the quality of the work done, clearly. I'd like to associate Chloé Segré-Tardif and Saladin Cabot, who made significant contributions to the project. But you have demonstrated scientific rigor, exceptional analytical skills, and you have evolved with remarkable autonomy, but while remaining constantly receptive. So you really impressed me. I'm really proud to see that the project, despite the growing difficulties for young researchers and global research in France, I think, has come to fruition. So it's all more precious to be able to celebrate such an achievement. So I congratulate you, Thibault, on behalf of myself and the entire Groupe Créative.
Thank you very much. Now the last supervisor, François CHAUMETTE.
Yes, thank you very much, Olivier. So I will repeat with my words what has been already said by Eric and Antoine. So first of all, I would like to thank very much the jury members, external one, of course. Even if Olivier didn't ask yet his question, you survived to the question of the external member. I think you can be proud of this jury. I think we have been able to select, to request some real experts in the different field of your thesis. And the fact they agree means something for you. And the fact they work to read your PhD, to write reports, to ask excellent question, difficult question, means something, I think, for you. So thank you very much, Steve, Hélène, Patrick, and Olivier. Then I also would like to thank the Creative company, because without this collaboration, in fact, you would not have done your PhD with us, and it would have been a real pity. So thank you. Then let's go to you. So as Eric already said, it is clearly your PhD. And I also would like to add that you started from scratch. And when we see the results you obtain after 3 years and a half, I really feel it is extremely impressive. Usually, my PhD students, they benefit from a very strong background in the field. They benefit from the V software, and in your case, it was not at all the case. So really, it is quite, it is extremely impressive. Then Eric spoke about we were outside of our comfort zone, and indeed, I confirm, and it was unusual for me. During all your PhD, I was uncomfortable. Not at all for you, not at all because of you, not at all because of you, just because of me. Because really, I'm convinced that I didn't serve at all from a scientific point of view. And I don't like that.
Not true.
I have the feeling to be a coach, just to encourage you to pursue it, to be a fan. And so at the end of the day, I'm very happy. But it was not easy because I'm not used for that. I think maybe my former PhD student can complain that I put them too much pressure about the writing of the paper, typically. Maybe Eric can confirm. So, and really, it was not the case with you. So you are one of my latest PhD, and it was a very original experience for me. And then I would like to say that I would like to speak about your qualities. So once again, as it has already been said, it is your ideas. You have, I think, good ideas, even if I'm not sufficiently expert to say that your ideas are good. But from I have seen from the discussion, I think they are. You already have 2 papers accepted, and we hope that the next one will be also accepted only. So it is your own ideas. I've been also impressed by how you have been able to take into account all the state of the art in this huge area, mapping, planning, and all that. And once again, from scratch. Your quality, your efficiency. When we say something, small idea, you are able to take that into account in few hours. I don't know if you sleep sometime. And the writing quality, also the curiosity you have in other fields, in politics, about climate change and all that. I appreciate that, is that you are not only focused just on your topic. And so all that is very good human qualities. So in my view, you have all the quality required to be a brilliant researcher, and I strongly hope that you will become a researcher at the end.
Thank you very much, François. So, yes, sorry, I kept
Let's go back.
the question for me. Thank you very much. And after it's done, after we have to. So first, let me join some of the remarks that was done previously. So I was quite impressed during your reading your manuscript by the quality of the figures. It can show clearly that you spend a lot of time on doing them. And what I also appreciate is that in the work you did, is sometimes it's very easy either to get stuck into beautiful mathematics, you know, making problems and just trying to see if they are sounding. And what I like very much is that you find the right balance between this formulation and trying to really solve the real problems on that part. And I really appreciate that. Also, actually, saw that you built also the 3D printing part on the paper robot. I think next, I've been working on Aldebaran robotics robot, and I understood what you went through. So I appreciate this also. So the thing then is that I will dive into a small thing. So small details after general comment, which is I was surprised that here in this lab people were doing planning, and I like
Peaceful.
and I'd like to thank very much Eric and François. So first for inviting me, yet also let you go into this direction of planning, which I think for me is that if you succeeded in making them doing planning, wow, that's a feat. That's a feat you should be proud of. No, in terms of technical question, sorry, so a lot of has been said, but I'd like to ask you some question about. So, for example, in slide 32, it's much more asking for explanation more than stuff that I didn't understand.
This one.
Yeah. So going back to the connected components, so we see a lot of components which were not connected.
Yes.
And so the reason is that
Such as this one, for example.
yeah. And in your PhD thesis, so maybe I didn't catch it. You said that you had a procedure to reconnect, if you could, some of these connect components. So
This was in the first, so the sampling-based method. I had a way to check for disconnected components if they could be connected by a string of a string of bubbles, let's say. But here in this one, since it's all deterministic, if I have some disconnected components, I just keep them in the graph, but they are never reached because if they should be connected, there should be a skeleton edge linking them to the. For example, as you can see on the right, these components are not reached by the paths which are starting from a single source, and I'm not really handling them in any way. I'm just getting rid of them, let's say.
yeah, but here, for instance, it's not very clear. So, for example, if we kind of zoom in, it looks like you have some unknown part inside the map and some obstacles. So, for example, it looks like if we take on the one on the left, what I didn't get is that what is it? It looks like it's a cylinder. So it looks like you are inside the cylinder, or you view all the cylinders. So what happened here? This is one of the problems that, for example, from a pure probabilistic viewpoint, this is typically the kind of map where you could do filtering. And for example, using morphological operator, I would guess that most of this stuff would have been either eliminated or closed. And then you could have connected the components, no?
Yes, I see what you mean. Yeah, maybe yes. I didn't try it on these maps specifically. In the previous method, I had a pre-filtering step on the sign distance field, not on the. Let's see, this one actually. Yeah, I have a pre-filtering step on the sign distance field, which is an erosion and dilation to kind of try to avoid the very small variations along the walls or stuff like that. But yeah, in the end, it could have been connected, but if it's not connected, it means that you cannot you cannot find bubbles which arrive to this component with the radius. It's also because of that. Maybe it's because I put a minimal size on the bubbles that I put in the graph. And so if a bubble, let's say if there is a skeleton edge which exists, but for which the clearance is too small, it's not going to be part of the graph because then it would be unsafe. And so that creates also disconnected components on each side of narrow passages which are too narrow for the robot to navigate safely, let's say.
Okay, thank you very much. I have also one small question. Something that, again, so what we can see clearly is you did a lot of things. You have 3 variations of your algorithm. In some parts, you do filtering, others not. So sometimes it's a bit difficult to get the whole picture. So I think you have a slide, I think, where you, sorry, yeah, I think page, yeah, so this is exactly this other ones, but we can see the bubbles, and so you have 4 comparisons. Sorry, I forget to note them. So maybe page 676, sorry, in your manuscript. Yeah, sorry. So it's another question. I apologize. I'm gonna go to this. This is connected. So this is something that I didn't quite get. So I did a bit of work on this direction, but I didn't work as intensively as yours on this one. But what I would expect is to have, for example, so we had the same kind of premise. How do you want to maximize the acquisition of new information, and at the same time, because you don't want to go back and forth. We had a humanoid robot, so that was super important for us to avoid the unnecessary motion. So I understand the path length. What I didn't get is that, so I would have expected that you would, some of the position where you acquired information would be in the boundaries of what you see, and then what will change maybe the direction where you are going. So could you explain a little bit more how you find the path inside the unknown area with the blue path? This is some, I didn't quite get the.
You mean the one on the left, which go into unknown space?
Yeah, exactly.
So yeah, here the way it's planned, so it's this iterative search for from the current position, and so basically here the unknown space is considered a priori free, so that's why the graph is the planning graph is present in free space and unknown space simultaneously, and so that's how the path can be planned. I think that's how we can go directly into unknown space.
It's a very optimistic assertion to say that it's free because it's unknown.
Yes, but so here, since we have a LiDAR in this setup here, it's not unreasonable to expect the LiDAR to detect any obstacle intersecting the path before we navigate it. And so, yeah, so just to finish so here, for example, it reached a third stage where it has to look at a very wide range of sorry. Let's say it's looking for paths up to 20 meters long, which are reaching a frontier. And so here, the frontier bubbles, we see that there is one, so every target of a path is a frontier bubble, let's say. And so that's how the paths are defined. I don't know if it's a very clear answer, but.
Okay, thank you. Maybe one last question, if I can find back this the slide. So yeah, so slide 47. Okay, so this is where I get a bit lost too. It looks like here again you have bubbles in the unknown area. Yes. And I don't see how they are connected with the other graph, where this don't seems to be so.
Who is the one we were discussing before, or?
So it looks like on the first part of your talk, when you speak about exploration and on the system, we can see all the bubbles. They all are inside the known place. And here we can see it's in the black part, the obstacle part, if we can use it.
Okay. So here actually it's because I'm representing it in the information map, and so it's not the occupancy map here. It corresponds to the occupancy, which is here. So you can see that the obstacles are actually on the walls. And so when we switch to the information map, since the path trajectory is only inside the existing walls, nothing outside of the walls has been observed. So it's free. It's a priori free because it's unknown, but it's not. It has not been observed, and so it contains full information. And so that's why, for example, the bubbles, which are completely outside of the walls, they have a very high reward score, because if you would be observing from the center of this bubble, you would see only new information completely. And while the one which is in the center of the already observed space, well, this one has a very low score because you would be looking at only stuff that you have seen at least partially before.
Okay, so and also this one is interesting also because it looks like what I like in your bubble representation. It likes, as it was mentioned before, I was under the impression that it's a kind of a very sparse coverage of the space that you're exploring. So here it's in the information space. Before it was inside the Euclidean space. And I think in some of your previous presentation, there is part where we can see that there is no coverage. So for example, here, there is almost nothing left. So for example, you see when you're inside the corridor, it looks like the space which is not covered by the bubble is far less than what you have on the left.
Yes.
And what I didn't get is it looks like you have a kind of so do you have an algorithm trying to maximize the coverage, or is it a kind of implicit results of your acceptance of the edges that you have inside
It's
the
only
system?
implicit, yeah.
It's implicit.
Yep.
Okay.
Because the sampling of the bubbles is only dictated by the skeleton. And so as long as we have skeleton points available and not covered, we sample a bubble there. But as soon as the skeleton is entirely inside of the bubbles, we stop sampling, and then it's only due to the connectivity between the bubbles.
You could sample on the skeleton and still have the criteria on the coverage of the space.
Yes, true. Yeah, I mean, yeah, but my so my order of sampling is determined more by the size of the bubbles than by their. So in a sense, it's true that I favor. It's more in the order of sampling than in the local choice of where to put the bubbles. But I'm always starting by sampling the biggest possible bubbles. And so, for example, yeah, at an intersection, I'm going to show it on the screen, but here at intersections like here, for example, you could have multiple choices to be on the skeleton and to have a bubble which covers the intersection, but here I'm going to take the biggest one because my assumption is that I want to have the largest possible bubbles at any point. So, sorry, are you kind of implicitly minimizing the number of bubbles that you put inside the system, or am I mistaken? I'm not sure it's the same, but yes, that's. Again, sorry, maybe it's me who misunderstood some part of your. Oh, in a sense, yes, but it's because so what I'm trying to do here. I come back to the skeleton definition. So since I have the information of the skeleton and simultaneously the information of the sign distance field, by combining them both, I know for every skeleton point what would be the size of a bubble that I would place there. And so I'm only adding them in radius descending order by starting by the skeleton point, which has the highest possible radius at this point. So, okay, so maybe the complexity is related to the number of points in the skeleton. Yeah, exactly. So yeah, but it's true that since I'm placing the biggest bubbles first, I'm eliminating as many points as possible from the skeleton when I place one, because when I place a bubble, I eliminate all the skeleton points which are inside. Yeah, sorry to be a bit picky. Do we agree that you are taking points inside on the edges? Okay, and then yep. Basically you have a continuous space where you could choose some of these points. No, it's pixel-based. Ah, okay, it's pixel-based. Yep. So you've got also the grid, so it's also depending on the parameter of the grid. Yes. Okay. Yes, so it's true that if I'm mapping at a resolution which is very close to the smallest opening I want to characterize, then it kind of fails because the bubbles become of pixelic size in a sense. Like they only cover a few pixels around them, and then the resolution is not enough to apply correctly the overlap condition. Is kind of I don't know if I'm clear, but the method becomes worse and worse as the map resolution gets worse and worse as well. I mean, it gets higher or lower when you look at it, but okay, no, because with the formulation, I thought it was like continuous, that from the skeleton you are actually taking the intersection, and then you had only a kind of continuous formulation of the edges in the skeleton space, but it's not the case. You stick with the grid part. Yep. Okay, thank you very much for this. Sorry, I'm almost done.
two open questions. One is so we are doing bipeds in the group, you know. And I see some of the reason why there is a mix between configuration and workspace, because we used to have the root base inside the configuration base, and this for you it's mixed with a workspace that Professor Lavallée was mentioning. So I get the point. So I will go into the other direction. Do you think that we can extend your work to quadruped robots?
Yes. It's, I mean, it's in my work mostly consider the mobile base as a very generic agent without any consideration of its, how it is driven. And the quadruped robot seems to me like it's okay to be approximated by a disk or a sphere for collision checks, at least with the environment. And so the only question is how well the SLAM behaves when the sensor is on the quadruped rather than the right base, but that is not that's like a prior problem to what I'm doing. So I think if the map is constructed by a quadruped, it should then the navigation plan and all the difficulties of using a quadruped with this method are actually in how to execute the plans rather than how to plan them, because I don't see a lot of HQs with the pass-I planner. They could be followed by a lect base without too many issues, I think.
The planning would be different, I would say.
Then you need to have a kind of a next, I mean, a planner, a low-level planner which takes the navigation path and plans the next motions accordingly. But it's more of a low-level problem than the method here. So this would remain valid as the oversight planner, let's say.
Agree. Last question, I swear. You didn't mention anything at all about learning, and it's a bit difficult to not talk about it right now. Do you think that, for example, I was wondering if you, so I have seen a lot of people, for example, learning depth map or 3D information optical flow. Do you think that it's applicable for the the distance function, or it will not scale up?
So I don't know exactly for this application here, but I did when I was doing my internship at LAS, we did learn some sign distance fields for the robotic joints. So it was a particular distance field, but we learned it with multiple methods. We found that neural network was the best approximator for this kind of stuff. And yeah, it's doable, but here the difficulty is that the distance field is changing over time as the map is updated during exploration. And so I don't know how, I'm not aware of a good learning algorithm, but also I'm not an expert at all on this side, so it's just, yeah, I'm not aware of a learning algorithm which is able to adapt as fast as the slants we have now to construct the map, let's say.
Thank you very much. So I think we are done with the question, unless some member of the jury have new question from this? No? So thank you, and we will move to another room for deliberate. Thank you very much.
So Patrick, we will start the Zoom link in 5 minutes, I would say. Thank you.
Ah, pardon.
C'est pas grave, t'es pas obligé, c'est pas le président.
So maybe the member of the jury, we can come in here in front. It's okay. So, Mr. Thibault, Noel, the jury appreciated the clear presentation that show your very good pedagogical skills. There were numerous subjects, and Thibault, you show that you were able to give a thorough overview of your work, as well as the context in which it was done. This presentation has shown your algorithmic contribution, as well as the experimental ones that everyone appreciated. You have demonstrated clearly the interest of your main contribution, the bubble representation, on perception, planning, and exploration problems. The answers you gave to the question from the external reviewers show that you are very knowledgeable in the area of your PhD. More impressively, the supervisor comments demonstrated that your independence in the scientific choices that you made. Indeed, the subject and the scientific direction were outside their usual expertise. And therefore, the jury appreciated that the algorithms were shown to work on real robots with scenario very close to the one that the industrial supervisor was considering. In the light of the fact that the PhD covered a wide breadth of subjects, you have shown a deep understanding of the control planning and perception topics. For all these reasons, the jury is delivering you the title of Doctor de l'Université de Rennes.
Can I do it in French?
Yes.
À l'issue de la... Non, pardon. C'est bon. En présence de mes pairs, parvenus à l'issue de mon doctorat en 2025, et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel que soit le secteur et le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Merci.
Congratulations.
Physically, but the spirit is there.
So if you want to say a few words,
Yes.
this is now.
I would like, so first to thank, of course, the members of the jury, both those who could come here and come and only online, but thanks a lot for your sort of review of my work and your very interesting questions today. I would like also to thank my supervisors, so François, Eric, and Antoine. Even if you say you didn't have a huge contribution on the scientific side, I would disagree because even if it was not directly on my methods, you provided a good background and you always made me think in the right direction to improve what I was presenting. And thank you. So that's more for François and Eric, and for Antoine, thank you for your help in keeping the PhD organized in a timely way, and having some constraints sometimes is also good to keep going. I would like to thank Groupe Créative for enabling me to conduct this PhD. Actually, without involvement of Creative, I wouldn't have been able to conduct this research. And from what we see today, I think the results are pretty interesting, not only for the company, but also for the research in general. And finally, I would like to thank my friends, my families, and my colleagues from the lab who were all very supportive during this 3-4 years. Especially the last 2 ones have been a bit harsh, have been a bit absent sometimes, but you are all always there for me. And it helped a lot to get through it. So thanks a lot.
T'as pas l'air récent. Tu vas annoncer ton pont peut-être, je sais pas si
Oui.
tout
Oui, there is I'm going to do it both in English and in French. So the pot de thèse, so we drink together. It's going to be at 4 this afternoon in the Salle Saint. And then tonight we can meet at the bar, probably at the Big Delirium near Satan, around 9. From 9 we will be there with my friends. So you're all welcome to come drink with us to celebrate. Thank you. Je peux venir au milieu si vous préférez. C'est toi qui choisis.
So, peut-être, est-ce que vous voulez qu'on se décale pour être plus proche du...
Ah oui,